Next, we're going to look at solving rational inequalities. So we've already looked at solving inequalities, and if you recall, with an inequality, we can compare it to a number line. We're trying to find specific values of x that make an equation statement true. So in this case, we're going to be looking at two rational functions, and we're going to be using our inequality signs to determine if the statement is true. So for this first one, we're asked to use the graph to solve when x minus 6 over x plus 3 is greater than 3. So we have two equations here. So if you take a look at the graph, we have a rational function and we have a horizontal line. So our two equations in the red, we have y equals x minus 6 over x plus 3. That's this equation right here. We also have the equation y equals 3, which is our horizontal line right here. So we're asked when the rational function is greater than 3, not equal to, just when it's greater than. So we're going to look at our graph, and we're going to use our horizontal line of y equals 3, and we're going to identify when the rational function is greater than 3. So that would be for these values. Now the rest of the function, this part is below 3, and this part is also below 3, so we wouldn't include that. So we have to identify when is that. So if we identify, this is going up by 1s, so this would be at -7. So we're asked to use the graph to find when it's greater than 3. So we know from -7, and does it stop? What value would it stop at? Well, you'll notice because this is a rational function, there is going to be an asymptote. Where is that asymptote? So if we look at our function, we see that it's approaching some number and approaching some number. So where is that asymptote? So we could see it's approaching this line here. That's our asymptote. And that value is at -3. So what happens at -3? Well, now our graph is below this horizontal line. So when we write our answer, we're going to say that x minus 6 over x plus 3 is greater than 3 between the values of -7 and -3. Now, which brackets should we use? Well, we're not including this point because it's not asking when is it greater than or equal to 3. So we would use a round bracket here. And then at -3, well, we have an asymptote, so it's not including that point either. We'll also use a round bracket. And there you have it. This is our interval notation to solve this graph. Let's try one more. So this time we're going to use the graph to solve when x is less than 3 over x minus 2. So first thing we need to do is identify our two functions. So the first function, y equals x, is our diagonal line. This is y equals x. And then 3 over x minus 2 is our rational function, which is right here. So we're asked when is x less than 3 over x minus 2. So we're looking at when our horizontal line, the red line, is below the blue line. Okay, when is it below? So take a moment to yourself to take a look. So we can identify that up until this point it's below. where else is it below? Now, because this is rational, we are going to have an asymptote. So let's identify where that asymptote is. So we can see that our rational function in the blue is approaching but never touching 2 right here. So this is at x equals 2. Now we have an asymptote there. When we have our asymptote, we know that this function is going to continue to increase on this side and continue to decrease on this side. So are there any other intervals when you see that our y equals x is lower than the blue function? Well, from here to here, it's also less than. So how would we write this statement? So up until this point, which is -1, so we would say from -infinity to -1, it doesn't include -1. And then what else would we say? So this point is 3. This is 1. So we would also say from 2 to 3. It's also less than the rational function. So in this case here, we have 2 intervals that we're using because since it's a rational function, there's changes. At this point here, the function is actually greater than the rational function, or y equals x. And then here onwards, it's also greater than. Okay, so that's how we would use the graph to verify if the equation is true and when, for which x values it's true. Now this time, algebraically, we're asked to solve when x squared minus 4x plus 4 over x minus 4 is less than 2. So the first thing that we're going to do here, we are going to solve for x. So we have x squared minus 4x plus 4 over x minus 4. And we're going to bring this 2 to the other side. So now we're going to have minus 2 less than, there's nothing left on this side, so we have 0. So now, because we're dealing with a rational function, remember this is over 1. So we're going to find a common denominator. In this case, we have x minus 4 and we have 1. So what we're going to do, we're going to multiply this side by x minus 4. Okay? And this side is just being multiplied by 1. So now we're going to have x squared minus 4x plus 4 over x minus 4 minus 2x minus 4 over x minus 4. So keep in mind when we distribute, we're using -2. So when we distribute this, make sure you're taking into account the negative. That's a common mistake. So now we have x squared minus 4x plus 4 minus 2x plus 8 over x minus 4 is less than 0. And now we're going to simplify. So we're going to collect our like terms. So we're going to end up with x squared minus 6x plus 12 all over x minus 4, which is less than 0. So we want to solve for x. So in this case here, if we're trying to solve for x, as you can see, we have a trinomial in the numerator. Let's factor this trinomial. So on the side, we're going to factor it. So we're going to take x squared minus 6x plus 12. And I'm going to use quadratic formula here. So our a is 1, b is negative 6, c is 12. So we have x equals 6 plus or minus 4 times 1 times 12. Oh, I missed a number here. 1 second. X equals 6 plus or minus 6 squared minus 4 times 1 times 12 all over 2 times 1. So as we simplify this, you're going to notice that we have a negative 12, a negative number, under the square root sign. And what does that mean? We're going to have no solution. So if we go back to our equation here, we know that x cannot equal 4, because if it's 4, what will happen? It will make the equation equal to 0 in the denominator, which is not possible. So x cannot equal 4. Therefore, when x is equal to 4, we call this a critical number. In other words, this is a restriction. So we're going to actually check these restrictions. So our only critical number here is 4. So we know that at x equals 4, this function, because the denominator will be 0, it's going to be undefined. Now we're also going to check when x is greater than 4 and when x is less than 4. So when it's greater than 4 and when it's less than 4. So if we plug in a value for the numerator divided by the denominator, say we plug in 5, negative 5, and on this side we can plug in 5. Once again, it doesn't matter which numbers you use. I could use a 0, and I could use 5, as long as it fits the parameters. So when we plug in negative 5, the numerator divided by the denominator, we're going to end up with a negative. And then when we plug in 5, the numerator is positive divided by the denominator is positive, so positive. So we would say, therefore, f at x is less than 2 if or when x is less than 4. When x is less than 4. Okay, so for this one, we have two rational functions. We're going to solve when 2x plus 1 over 2x minus 3 is greater than x plus 1 over x minus 5. So in other words, I want to know for which values of x will this statement be true? Okay, so for which values of x will this statement be true? So we're going to take 2x plus 1 over 2x minus 3. We're going to move this rational equation over. So it's minus x plus 1 over x minus 5. And that is greater than 0. So now we need to find a common denominator. We're going to multiply these which means we're going to multiply this side by 2x minus 3, and this side we're going to multiply by x minus 5. So we end up with 2x plus 1, x minus 5, minus 2x minus 3, x plus 1, over 2x minus 3, x minus 5, and 2x minus 3, x minus 5. So now we're going to use FOIL in the numerator. Okay, and we end up with 2x squared minus 10x plus x minus 5 minus, and then we have 2x squared plus 2x minus 3x and minus 3. Now, don't forget we have to distribute this negative into all four of these terms. So then we have 2x squared minus 9x minus 5, and then minus 2x squared plus x plus 3. And this is greater than 0. So let's simplify this as much as we can, collect our like terms, and we end up with negative 8x minus 2 over 2x minus 3, x minus 5. So we need to see what the critical numbers are. So when is this going to be undefined? When will it be undefined? So when x minus 5, it cannot equal 0, so x cannot equal 5. And then 2x minus 3 cannot equal 0. So when x is equal to 3 over 2, and then the reason why we're checking this one here is not necessarily when it's undefined, but when it's 0. The reason why we're checking this one is because the equation says when is it greater than 0. So it won't be true if it's equal to 0. So that's why we're checking the numerator as well when it's equal to 0, because we don't want it to be equal to 0. We want it to be greater than. Okay, it would be different if it was saying greater than or equal to 0 is okay, but in this case it says greater than. So we have negative 8x cannot equal 2. So x cannot equal negative 1 over 4. So our critical numbers are here. And we're going to make our chart now. So for our critical numbers, we're checking. We need to make sure they're in order. So the first one is when x is negative 1 over 4. It's going to be 0. We have to check when it's less than. We need to check when it's in between negative 1 over 4 and the next highest number, which is 3 over 2. We know that when it's 3 over 2, it's undefined. We need to check when it's in between 3 over 2 and 5. we know that at 5, it's going to be undefined. And then we need to check when it's greater than 5. So I'm going to give you a moment to check those. Remember, you could use any value as long as it's less than. So you can use like -3, you can use 0, you could use 1, or 2, sorry, you could use here 2, and you could use 6. So you can pause the video and take a moment to check. So we should get a positive value here, a negative value, a positive value, and then a negative value. Now, the question asks, when is it greater than? So we're looking at the intervals where it states that it's positive. So that would be here and here. So for our final statement, we would say, therefore, the inequality is true when? When is it true? It's true on the interval when x is less than -1/4, and when x is in between 3/2 and 5. Okay, so we used those critical numbers. So 5, 3/2, but also -1/4, because it cannot equal 0 either. And when we use those, we're able to solve the inequality. So we could double check in Desmos here. So our first equation is 2x plus 1 over 2x minus 3. And our second equation is x plus 1 over x minus 5. So if we take a look at when this is true, when is it greater than? So notice here, it's greater than up until which point? Up until which point? Up until -0.5, which is one of our critical numbers. And then when else is it greater than? Well, it's also going to be greater than after this asymptote. So from here, so from 3/2 up until 5. Okay, so those are the critical numbers. And then what happens at 5? Well, notice we have an asymptote at 5. So I'll put my asymptote here. Okay, so this is the inequality. So when you're solving algebraically, you're going to solve and find the values of x for your critical numbers, and then you're going to use your chart to check when it's positive or negative depending on the statement, whether the statement is asking when it's greater than or when it's less than.